Speaker today is Jörn Grosse-Knetter from the University of Hamburg.
It's supposed to be as low as possible to not disturb following detector components. Now, speaking of pixel detectors in particular, later on, there's a little add-on, if you like, because we have the means of providing very good position information, in which case you can very precisely follow the tracks back to their origin. So that would be the bottom point of those tracks. Can you actually see my mouse pointer? Then I can actively use it.
Yes.
Oh, very good. So sorry?
Don't move it too fast, but...
Oh, okay. I try to do it slowly. So the intersection point of tracks is what we normally call a vertex. There can be two different vertices. One type is the origin of the collision, and that's what we call a primary vertex. What this type of detector, so the vertex reconstruction technique, is particularly used for is what we call B-tagging, in which case we reconstruct the distance that a particle lives until it decays, so like a heavy B meson, which has B quarks inside. That's why it's called B-tagging. And essentially, beta gamma tau is the distance that it travels, of course, following decay law. That will vary a lot. So we can distinguish B quark type hadrons from other hadrons, which you see on the next slide. So the left-hand picture is what we already are doing with the pixel detector in Atlas. And that's the so-called impact parameter. It's slightly different. You measure the distance of a track from the primary vertex. And if there's a larger distance, then it's a strong indication of long-lived particle, or semi-long-lived particle on the way. Long-lived in that case means actually picoseconds. So you have travel distances of 100, 300 micrometers, millimeter even. But still, well, you see on the scale up to a millimeter, you get the difference between B quark containing hadrons and light quark containing hadrons. So that's the idea behind it. So that is already established in the LHC experiments. Still, the technology is quite challenging. So quite a bit of what I say is working already, but I thought it might still be of interest to you. The future challenging aspect of this is we have already a high hit rate and density. So we have many tracks, that means many hits in our detectors. That comes along with a high radiation dose, or as you will see later on, mostly fluence is what we have as a describing quantity. So we have to make our detectors survive this and still provide useful data, and that will get even worse when we move on to what we call high Lumi LHC. So the upgrade of the LHC accelerator for increase in the luminosity, which of course then will come with an increase in hit rate and radiation fluence. So you see a scary picture on the right-hand side. That's a simulation of a high Lumi LHC event, which actually is already quite modest compared to what we expect nowadays. That has 140 simultaneous collisions from protons. Latest ideas of the accelerator people will probably even have 400 of these. So that picture would even look worse. And all those little spots you see there are hits in silicon detectors in the upgraded version that we plan for Atlas. So that's kind of the challenge that we're facing. Now, why silicon detectors? They are actually, as we will hopefully see in the course of the talk, well suited to this task, both high hit rates and radiation tolerance. So what is it in the first place? It's a solid state detector, which we can segment into sensing elements. I will tell you how that works. And this segmentation is crucial for the position information. Inside the detector, we create charge by ionization. That charge is read out electrically. Well, it's a charge, you can do it. So we need electronics that can do that. That will tell you in which position we had the hit. The position gives us a spatial information, which allows us to do the tracking. And the spatial information is done by segmentation of the electrodes, typically strips. That is for the outer parts of our tractor where the hit occupancy is not that high, and pixels for the innermost part where we have to survive higher track rates. And I will actually focus on the latter, but generally the idea of a large portion of what I will tell you is true for both aspects. So in that sense, let's have a very brief look at semiconductors, or actually mostly silicons, and how we can turn a piece of silicon into a detector on a more general basis, let's say. So I hope this is largely a repetition. If not, feel free to ask. So I assume some basic semiconductor knowledge will be there. So what is a silicon? Silicon is a crystalline structure, and the diamond lattice that we have has atoms that share covalent bindings, and the special energy level structure that forms comes in a band structure. So a typical valence and conduction band as we see it, and the electrons from those covalent bindings have to jump from the valence to the conduction band, which would be the ionization process. The energy gap that has to be covered is about an electron volt. Actually, for real ionization process, there's even energy deposited in the lattice. So for real purposes, it's more like 3.6 electron volts that we have to invest in order to ionize. So ionization for the electron means it's moved from the valence part, so the bottom part of the band, across the band gap into the conduction band, through which it can move more or less freely, not entirely, but to first order it moves freely. That leaves a gap behind in the bindings, which we call hole, and the hole can be filled by a neighboring electron, which you can interpret as a moving gap if you want, so a moving hole in that sense. And the hole does exactly the opposite of what the electron does. It jumps from the conduction into the valence band, and in the valence band, again with limits, it's more or less freely movable. And that's exactly what, the principle we make use of later on. Now, even though industry can make silicon in an unbelievably pure state, it's not entirely pure, and even so, with normal room temperatures at least, you have charge carriers in your silicon, which is undesirable because that's what we want to detect when it's created from an ionization process. Should not be there in the first place. The way you typically describe this, that you have a Fermi distribution, which spreads out over the 50% probability point, which is the Fermi level, and the higher the temperature, the more it spreads out. So for normal intrinsic semiconductor, as it's called, so one that comes with a nearly pure lattice, this Fermi level is more or less in the middle of the band gap, and the distance to conduction and valence band is more or less the same. What we will make use of to get rid of even those leftover thermally induced or created charges is doping. So doping means you had non-silicon type atoms which have one electron less or in addition, which creates so-called p-type or n-type semiconductors. P-type means we have extra positive charge carriers, so holes. N-type means we have extra negative charge carriers. That means electrons in addition to what is there from thermal creation. And you have one of those two types, so more electrons or more holes in excess. That's why they get this naming. In terms of the band description, that means the Fermi level moves either closer to the valence or closer to the conduction band. So your Fermi distribution reaches out further into one of those bands, and that means the extra electrons for n-type or the extra holes for p-type are, again, freely movable or around freely. So in order to get rid of the charge, we create a p-n junction, and what I just talked about concerning the Fermi level helps to understand what happens at the p-n junction. The Fermi level is sort of an equilibrium measure. It means if you have two different semiconductor doping types, those Fermi levels have to line up. Now you can imagine when one is closer to the valence, one is closer to the conduction band, the bands have to migrate somehow to make the Fermi levels meet. So in a picture on the next slide, you see what happens. So we have the n-type and the p-type doping, one with more electrons, one with more holes. And the Fermi level, which in one case is close to the conduction band for the n-type, will meet up the Fermi level of the p-type, where it's closer to the valence band, and then the edge of the bands will move over in order to make the connection. So physically what happens is that the electrons in the n-type migrate further away from the junction, same for the holes in the p-type. In order to make this possible, they're simply shifted away from the junction because the conduction band is more difficult to reach for the electrons, same the other way around for the holes. So what is left is a region free of charge carriers, and this creates a space charge, which in turn leads to an electric field, which you can measure. So it's basically the difference of the position of the Fermi level. So you can calculate this. That corresponds to what we call a built-in voltage or potential difference. So if you want the potential difference between conducting band in P and in N-type. The result is that causes a drift which counterbalances the diffusion from the two opposing majority types, and in the end an equilibrium is reached. So we make use of externally disturbing this equilibrium, so we deliberately shift the Fermi levels even further against each other by just applying an external bias voltage. So in some sense you increase the built-in potential that rearranges itself by this diffusion drift process, and you can shift those two bands with respect to each other even further. That means you make the barrier larger or smaller, depending on which polarity you apply. So larger would be our case, and then the following happens. This region that is free of freely moving charge carriers, so the space charge region, if you like, or which we call depletion region because it's depleted of charge carrier, grows. And there's a preferred direction where it grows, at least in the way we build semiconductors nowadays for our detectors. So the idea is that you have a substrate, so in the end, physical wafer, which has a relatively low doping, so the concentration, numbers of donors, let's say, per volume is very low. So in this example, it would be 10 to the 12 per centimeters cube. And on top, you add another layer of opposite doping. So in that example, when you have a substrate which is lightly n-doped, you would add a p doping on top, which has a much higher concentration. And there's a reason for this, and it's not because we can't do better. In the end, this entire device has to stay neutral. So when you have this recombination of electrons and holes on either side of the junction, they have to combine one by one. One hole gets one electron, and then you're left with a space charge. That means in the part of the device that's weakly doped, you have to evacuate a much wider volume of charge carriers than you would have to in the highly doped part. So in this example, the depletion zone, so the zone that is free of charge carriers, would grow into this in the substrate, which is what we want. We want to have as much volume available free of charge carriers as possible, and growing into the substrate is good. So what you see in the end is, well, maybe let's go for this. So the electric field that corresponds to the space charge would then mostly extend into the substrate. So in other words, what would our detector now look like? We have the substrate, so that's more or less a chunk cut out of a silicon wafer. This non-colored part is the lightly doped bulk. Then at the bottom, in that case, we have the p-type highly doped part added. So at the edge of both, we would have a p-n junction. We apply an external voltage, extract all the intrinsically existing charge carriers so that the entire bulk is free of natural charge carriers. So now comes our charged track particle, so something from the LHC, proton, electron, what have you, will create new charge carriers. That is still possible. You can still ionize the lattice. So we have fresh electron-hole pairs, and they are now noticeable because there is no charge left. There is a charge or cloud, if you like, available that is now distinguishable in this evacuated region. Now, it's not the end of the line. We're still within the volume of our silicon, which well, is not very useful for detecting something on the outside. We have to get to that charge on the electrode. So there's a bit of add-on feature that we have to talk about, which is charge carrier transport and signal formation, which I will come to now. So charge carrier transport is easy. I already claimed electrons in the conduction band and holes in the valence band can move around more or less freely. Not quite, but almost. And we can make use of that. We already have an electric field. You saw there's an electric field created by the depletion zone mechanism, which is even increased by the external voltage we need to extend the depletion volume. And that, of course, will accelerate our charge carriers, both electrons and holes, in opposite directions, obviously. There will be remaining collisions with the lattice, or well, for holes it's even more complex because they have to fill the gaps and they don't get or move ahead that quickly. So the combination of both results in at least on average, more or less constant velocity, which is proportional to the electric field. There's a little difference between electrons and holes. This proportionality between the drift velocity and electric field is described typically by mobility. You see in the plot there's a part where the mobility is independent of electric field. Holes have a smaller mobility than electrons, which is simply because of what you call effective mass in a semiconductor that is higher for the holes. That more or less reflects that filling bonds by electrons, which is the effective moving of a hole, is a bit more difficult than for the electrons. But even for the electrons, the effective mass is not equal to the free mass. So that has to be taken into account. But generally, that's the simple model. You have the charge carried around from your ionization. We have the electric field that is already applied. And as a net result, we'll get the electrons and holes drifting towards the electrode, towards the opposite electrodes to be precise, because they have an opposing charge. Holes are positive, electrons are negative. So the other aspect is the signal that we want to measure. So that's how we detect in the end. Well, a very simplistic picture would be you simply wait until the electrons arrive at the positive electrode, the holes arrive at the negative electrode, and then you see them. It's not quite like that. So you probably remember from your introductory lectures, a charge placed in front of a metal plate will induce surface charge on that metal plate. So the metal plate in our case is our electrode. Actually, physically, you normally have a metal layer on top. And the same will happen here. Our moving electrons and holes will induce charge there. So as soon as they're separated, they're actually in different positions. So the induced charge you see from them will be different. There's an entire theorem around this. Shockley-Ramo had a calculation. It's basically standard electrostatic calculation. And the induced current effectively that you see, because charges moves, the induced charge will also change, and change in charge is a current. So the induced current that we see on the electron is basically a vector product of the drift velocity and something that's more or less derived of the electric field, but without the charge carriers in there. So it's basically your detector electrode field configuration, if you like. As an example, for a parallel plate capacitor, so two opposing flat electrodes, the electric field is U divided by the distance d, and the weighting field, as it's called, or the Shockley-Ramo field, is just that field normalized to the voltage, so 1 over d. It's more complicated for different electrodes. I come to that. So anyway, our task is to detect and integrate the current, and the total integrated current is the created charge in our semiconductor. That's what we want to measure. So that's something we have to keep in mind for the electronics. And only both together, separating the charges by electric field and measuring the induced current, will give us the detected the signal that we're supposed to detect. So life is a little more complicated, at least for pixel detectors, in case of small electrodes, where small means they are small compared to the total drift distance that our charges have to travel. The weighting field isn't quite as simple as what I had for the parallel plate capacitor. So basically the same electrostatic rules, which tell you look at the field that has a voltage only on the electrode you're looking at. Solve Laplace equation in the end, or Laplace equation that will yield what you see on the top left plot. So that's actually the potential. If you want to go for the field, look at the difference between the equipotential lines, and you will see the electrode that would be at the bottom here. The top is a uniform opposing electrode. The weighting field is not homogeneous as you would have it for a parallel plate detector. It's very large, very close to the electrode, and most of the volume actually has a very low field. So consequence of this is you can't just measure all the way through or even stop on the way because you integrated enough current on the way. We have to get our charges very close to the electrode. Only then the induced current that we see will be noticeable. And well, from then on, we still have to integrate to get to the whole charge. Keep that in mind. That may seem a bit odd now, but that's very important for one of the radiation damage effects that we'll see later on. So anyway, let's go back to the picture you've already seen and the two items in the text. So now we have an electric field. We separate electrons and holes from each other. You have a measuring device, some electronic circuit on one of the electrode to read it out, and the induced current is integrated. And that is the main detection mechanism. A bit boring for now. That would be something like a photodiode, for example, or a dose meter if you want, nothing more, but still that's the main detecting mechanism. A bit more extensive than what you might have seen already, but we need a few of those details later on. So Now, the boring means it's not segmented so far. We have to do a bit about getting to that point. That on paper at least, or on slides, is very simple. You segment one of those electrodes. Well, for a gas field detector, so your favorite, let's say, Geiger-Müller counter or proportional counter, that's easy. You segment your metal electrode and you're done. Well, semiconductors are called semiconductors for a reason. They are conductive to some extent, so segmenting an electrode doesn't do the job. They would be short-circuited, and you would not see any segmentation. So we have to go one step further. It's relatively straightforward when you think about it. One of the extra doping layers that we add to our bulk. So again, this square or rectangle thing is the bulk. The red layer is what we applied as opposite doping, and we can add some structure when we apply it to the doping. I will tell you later on how that works. So each of those strips in that case form a separate p-n junction, and between the p-n junction and the bulk, we have a depletion zone. The depletion zone is free of charge carriers. That means they are isolated, and that's what we need to achieve. So each of the strips in that picture are isolated from each other. Then, of course, on top you add a metal layer, and there you have your segmentation. That's the only way to get it in a semiconductor. Technically, that can be done with a mask when applying the extra doping. So now, next step is, of course, then to connect each of the strips to a separate readout electronics device. And you can read out channel by channel, and the channel that fires, so in that picture, the one with the yellow triangle here, the yellow amplifier that would see, for example, the holes, would tell you there was a signal, and if you made the pitch, so the distance between the strips fine enough, you get a decent position resolution. So technically, you can achieve something in the few 10 micron order, and by simple statistics, you can calculate that the position precision of a hit strip with P would be P by square root of 12. So for example, for a 50 micrometer pitch, you would get to 14 micrometer resolution in that case, which is fairly decent. So you can do decent tracking and vertexing with that. So strips have a bit of a problem when you have a high track density. They may be small in one direction, so in the pitch direction, but they're normally long in the other direction. That's why they're called strips. So you're talking about centimeters. So in total, they have a very large area. And when you have a high track density, each of those strips get hits very often. When you cross those strips, which you have to do in order to get a full 2D information, there might be ambiguity. So strips normally apply to not too high hit rates and densities. So that's where pixel detectors come into the game. So for one thing, they have a 2D hit information right away. And as the hit probability for the same particle fluence, let's say, goes per area, a smaller area, which you get for free from a pixel electrode segmentation, reduces. So you have much more time to digest the hits on an electrode, which is good. There are a few more extra benefits. There's something which we call leakage current. So within the bulk, you still get electron hole pairs generated thermally. Of course, they are constantly extracted by the applied external voltage and generate a constant current. That's what we call leakage current. That goes with the volume. The more volume you have to create electron hole pairs thermally, the more current you get. So small electrodes are actually beneficial in terms of that. That's even better for noise. That's in electronic terms, essentially because you have smaller electrodes. Smaller electrode area means a smaller capacitance, which is beneficial for the electrons. The complication which will make the technological challenge for pixel detectors is you have to connect a reader to each of those pixels, which can be hassle. On a small area, you easily get several thousand channels that are read out. So otherwise, the sort of straightforward pixel detector works in the same way as a strip detector. You have your opposing doping layer segmented, so they are automatically isolated. There's a little trick to which we come back later on also in terms of the radiation damage. You can also segment the opposite type, which I should maybe briefly mention. So that's colored for a reason. The opposite electrode has to be connected in any case because you need two electrodes in order to apply a voltage for the electric field and for the depletion mechanism. Now, adding metal to semiconductor is a bit peculiar. That forms something we call Schottky contact, which is also rectifying, which we don't want. And the Schottky contact is also barrier, so similar band model as you saw it for the PN junction. And the width of the barrier can be reduced by increasing the doping concentration. So for that reason, you normally add a very high doping concentration of the same time in that case on the other side of the bulk, just to have good ohmic contact to the metal electrodes. So since you do some doping on that side anyway, you might as well segment that. But now the problem that I mentioned before comes into play. That would be short-circuited because, well, in that example, you would have N doping on N bulk. There is no automatic PN junction, so you have to add it manually. So typically you apply an extra P doping between your pixel electrodes, but then you can also segment the opposite side. That's an interesting feature. Again, please keep in mind, comes back later. So, well, for now we stick to pixel segmented electrodes on a bulk, whatever way. And well, in a way we have to connect each of those pixel electrodes to electronic processing circuit. And that's the tricky part. That's where this hybrid pixel detector concept comes into play. This one-to-one connection can be realized in a way in which you make the readout chip. So you have a dedicated readout chip with amplifier and so on, in which a pixel cell with a full amplification mechanism circuitry matches the size of a pixel on the sensor, and then you connect them one-to-one. The sandwich is why we call it hybrid. And now I will tell you how we make basically and design these two parts, the sensor side and the readout side, or readout electronics chip if you want, and how we connect those two parts in order to make it work. So let me start with the sensor. That's what we've been talking about already. Intuitively you would say, well, silicon is very common in microelectronics, so go to industry, ask them to make your wafer with as tiny as possible pixel electrodes or whatever suits you. However, this will not work. Microelectronics normally uses a bulk that has a relatively high doping concentration. Now remember, we want to deplete our bulk as easily as possible, and that is possible with a low doping concentration. Actually, the doping concentration directly reflects the amount of voltage you have to apply in order to deplete it. So the lower the doping concentration, the lower the voltage you have to apply. And high voltages are always a bit awkward and technically difficult. So that excludes generally microelectronics. The other problem that you would be facing is that microelectronics just cares about the transistors, and they live in at best few micrometers on the surface. They would not care about the rest of the bulk. However, for us, the bulk is important. That's where our detection happens. So we have to take care of that. So special production mechanism had to be established and are established by now. You need industry process that can consider the complete volume and, as you saw, also the backplane, because we have to connect the other side, which is not segmented, in order to apply the electric field. The doping concentration has to be low, or high resistivity as it's often called, same thing, in order to reduce the voltage we need for full depletion, which in that sense requires a production mechanism for the entire silicon rod ingot, as it's called, for which we normally have a float zone mechanism. Industry uses something that's called Tucholsky, which is difficult for creating low effective doping. So maybe a few pictures to make a bit more colorful. So in the left picture, you see what a float zone process is. You have a rod of silicon that's normally just polysilicon, which is not suitable for semiconductor purposes. We want single crystalline structures in order to get a proper bent structure without any impurities. So you take that rod, you heat it up locally, and while it's heating, all the impurities go and the silicon forms itself again as a single crystal. Now, given that a large portion of the impurities are extracted, or they melt down at the bottom container, you automatically achieve a very low doping concentration, which is exactly what we want. So that's why we use a different production mechanism than the microelectronics. So Tucholsky, that's what they use, is more or less like drawing a candle. You dip a seed into a molten phase and pull it out and let your single crystal go one by one. That's more difficult for getting low doping concentration. So then you cut that ingot and then that rod, you get slices, and that's what you see on the right-hand picture, and that's what we call a wafer. And then the wafer is processed with further doping. So that wafer would be what I call substrate or bulk. That's your homogeneously low-doped N, or if you like, P-type substrate. So then comes the creation of pixel elements. So we go from top left to bottom right. Initially, you have the wafer with a bit of oxide that will form, if you want it or not, naturally. And then the most important part in the process is adding what we call a mask. You have photoresist, something that's photosensitive. Maybe if some of you knows how to make printed circuit boards, that's the same idea, just on a much smaller scale. You have some photo wafer, if you want, that's transparent to light, except for the places where you want to get rid of the photoresist on the wafer. So, for example, in the places where you want to create your pixel implants. So you illuminate the photoresist with this mask, etch it afterwards. As a result, you get a hole, which is penetratable by external particles, and that's what we do for the doping. So it's an external implantation. You shoot boron or phosphorus typically for silicon in order to get acceptor or donor atoms that will later form your P or N-type silicon. And this is literally overwriting what exists already in the substrate. So we have an, let's say, lowly or weakly N-doped substrate. You simply add more boron atoms in that case to achieve a overdose of acceptors, so you get more holes than you initially had as electrons, and as a net result, that part of silicon will behave as a p-type, contrast to the n-type bulk in that case. So you can do the same to the opposite side of the wafer, which doesn't necessarily need segmentation, just for the contact. Then you add some metal on top in order to allow easy electrical contacts, and that would be the rest of the picture. Skip that. So that's the core part, how to create pixels in your silicon. So in real life, it looks like this. So that's a cutout of the picture you saw. That's cut through a wafer, looking on top of the wafers on the top left picture. That's 4 pixel cells. And what you see mostly is, of course, the metal contact. That would be where we later add our interconnection to the readout chip. There are some more testing structures on top. That's why a little corner is cut out. So that's a little cell in one of these sensors. You see an entire wafer, even with more complex structures in there, but one of these rectangular objects here, for example, that would be a sensor wafer with typically a few 10,000 pixel implants on top with a metal contact. So that's the first part of the hybrid. Second part is the readout. I will keep this short, but just to give you a glance. So we have one readout chip. That's one of these dark gray areas, which has many of these light gray areas on top. The light gray areas would be a pixel cell. That's of the same size as we just created the pixel cell in the sensor. Has a contact, of course, in order to be able to contact it to the sensor later on. And in that cell, you have to take care of an amplification circuit. So that reads in the induced current signal, does some sort of integration, and then hit detection and storage mechanism. That all belongs into the pixel cell. And at the bottom, with some sort of digitization, you digest those data. Typically in high energy physics, we have a trigger because we filter certain data. We don't write out everything that needs to be received compared to what we saw in the detection mechanism. Then data is typically serialized and written out on digital data links. Nowadays, it's very common to write that optically. So that goes along with the hit information plus a timestamp. That's very important for us. LHC, for example, has collisions with a rate of 40 megahertz. So every 25 nanosecond, we have a new collision. And if we can't tell to which of those collisions our electrical signal belonged, we will not be able to reconstruct any tracks. Of course, only hits from the same collision should be joined to a track, not from the following collision. So we need timestamp, which means we have a correct timing on the chip, which is provided, for example, at LHC with a 40 megahertz clock from the outside. So schematically, that looks like the following. You have the contact pad here on the left that is read in by an amplifier. The feedback circuit is a capacitor which automatically would integrate the current. So the output voltage that we get in the end is already the integrated current. So exactly the charge that got induced by the Shockley-Ramer theorem. Here's some possibly analog filtering in the end, a discriminator typically, which tells you hit or no hit. And just to give you a figure for 250 micrometer silicon, a typically high energy particle leaves something like just below 20,000 electron charges. So that has to be detected in this mechanism. In real life, looks like this. So that's a readout chip, in that case, from the LS experiment. You have most of the area covered by those small pixel cells. So they look like this. It's a rectangular shape in this case, 50 by 425 micrometers, with the connection pad for the sensor, and the rest of the electronics is hidden in that area. And several thousand of these pixel cells hidden in the main area, and on the bottom you have something to communicate to the outside. That means sending the data or receiving commands even to configure your chip. How well this can be done is progressing rapidly with advancements of the electronics industry. So even our experiments get better and better in that term. But that by itself is challenging. We'll not report about this today, but that is as challenging as making a sensor at least. So now we have two separate parts. One is detecting and providing a charge pulse in the end. The other one is digesting this and turning this into digital hit information that our experiment readout can digest. Now we have to connect those parts and really channel by channel, which means several thousand or 10,000 connections between those parts. For a long time, such high density connections were done with what we call wire bonds. So that's 20, 30 micrometer thin aluminum wires typically, which is connecting two pads with ultrasonic welding. In real life, that looks like this. That's very nice to connect outside pads, let's say from a chip, between chips to a printed circuit board or so. But remember, we have to go for a sandwich structure. And pulling wire bonds between these, well, is kind of delicate, if not totally impossible. So new technology had to be invented, which is the bump bonding. That is very closely related to what industry does. You might have seen this on modern digital electronics. It's called ball grid arrays typically. What we need here is even finer in terms of spacing between those connections, but the general spirit is the same. You have little meltable or compressible material on a contact pad, which you can solder literally to the other side of your sandwich. So that contains two parts in the process. The bump, that's this little electrical connection, is deposited mostly on one side, sometimes on either side. So let's say on the readout chip, then you have the sensor chip, which you flip on top, and in the end you solder them together. Typically it's solder bumps or indium, which is slightly softer material. And well, let me at least show you the solder bump techniques. So the philosophy is that you take one of those sides, again, let's say the readout chip, you have the contact pad that is shown here, and you add some extra metal layer on top because the material we normally use for the solder bumps is not suitable for the aluminum metal layer that we have on top of the electronics. That's called underbump metallization, which you see as UBM. Then the same technique that you already saw for the sensor production, that is apply a photoresist with a mask that illuminates, and you etch the photoresist in the places where you want to create the electrical connection. So that creates photoresist, that's this gray area here, and a gap in between right on top of the electrode. So with, in case of solder bumps, galvanic processes, you can add, for example, in the old days it was lead tin. Nowadays we've moved on for health reasons to tin silver. That will grow a little cylinder on top of the electrode. Then you remove the photoresist again to a reflow. That means you put it in an oven and heat it up, and you end up with a little solder sphere on top. In real life, we see in the top right picture what that looks like. So the contact is at the bottom and you have the solder sphere on top. This you can do with a pitch of up down to 50 micrometers, so the distance between solder spheres of 50 microns. So we are able to go down to pixel pitches of the same size. That's what we take advantage of. So the last part is what I call flip chip. You take that chip, so say the readout chip, flip it over and move it over the sensor chip, which also gets some extra metal layers on top of its pixel contact. You push it on top and again do a reflow. That means put it in an oven, heat up the solder, and you will get electric connection. And that over several rows and columns one by one. That's the benefit. Okay, well, maybe skip indium. So ideally, such a row would look like this. Real life may look more complex. Things go wrong, of course. So bumps may merge or may be missing because something went wrong with your photoresist. So that requires a lot of inspections on the way until you get it. Remember, we have several 10,000 pixels typically on such a sensor. So you have a similar number of connections. Well, with a bit of inspection, you can get a high yield. So in the end, we were able to go down to a loss of less than 1% on a few centimeter by few centimeter device, which is acceptable for a tracking device. And for example, what comes out is what you see on this slide as an Atlas Pixel detector module, as we call it. So a device that is standalone data taking, if you want. So in here, we have a sensor. That's the pixelated silicon device I showed you. Beneath, you have several chips in that case. Actually, you can't make the chips as large as the sensor. They are connected one by solder bumps. You see the little dots in the cross-section view. And on top, you have some services, basically a very thin printed circuit board, which provides power to the chip, bias voltage to the sensor, and connection for the digitized readout serial streams. So this device had almost 50,000 pixels, 50 by 400 micrometers wide. And to turn this into an entire detector, we have carbon structures on which these modules are glued. So each one of these very tiny rectangles here is what I showed on the previous slide as a module. The entire thing forms a barrel, which is then wrapped around the beam pipe in LHC. In the innermost part of the Atlas detector, we have 3 of these layers nested inside each other. On the outer side, we have more disks. So in total, we cover roughly an area of 2 square meters with pixel modules that in total have 80 million pixel channels. So you can imagine that's quite a challenge in terms of getting all the connections. That means 80 million bump bonds in the end, right? So this has been in operation for several years. We had a little add-on, which already goes a bit half a step, let's say, in the direction of high-lumi LHC. In the LHC shutdown 2012-13, we added a 4th barrel layer closer to the beam that actually literally meant directly screwed to the beam pipe that was replaced. And because it's even closer to the beam, challenges in terms of hit rate and radiation hardness increased even more. Could make the pixels smaller by then because the electronic had advanced. So we had with more than 200 modules with 50 by 250 micrometers pixels inserted in the innermost part of the pixel detector with adding another 12 million channels. So we have an almost 100 million channel Atlas Pixel detector by now. That is happily doing beat tagging and tracking for us. Right. Well, speaking of going into the direction of high-lumi LHC, one of the most challenging parts, apart from the bump bonding, is the radiation damage that we suffer from while the device is in operation. So let me go into this for the last part of the talk. So generally, there are 2 types of radiation damage which are created by the particles that we actually want to detect. So there's no way out. You get them from LHC if you want them or not. Actually, we want them. So we have to make do with the damage that they cause on top of the signal that, of course, we want to detect. So one type of damage is caused by the same mechanism. Charged particles create electron hole pairs, or generally ionized. That's the detection mechanism. On the surface where we have a boundary between oxide and silicon, this is actually inconvenient because in the oxide, the charges are not movable and they will do damage to the electrodes because they are on the surface, and also on the electronics. Same reason, electronics lives on the surface of silicon. However, I will not go into this today. We spent most of the time talking about sensors, so I will focus on the other aspect, which is mostly affecting sensors. That's what we call a bulk damage. So mostly heavy particles, that is protons, neutrons, to some extent even pions. They damage the lattice of the silicon itself, and that, of course, changes the properties of the sensor. In either case, in the end, the charge collection in the sensor or the processing of the electronics is affected, and that can go as far as potentially losing the signal, so not being able to detect the charge pulse anymore, and your detector turns blind, so in that sense useless for tracking. So that's something we, of course, have to avoid. In the description of, well, let's say the bulk damage at least, we have two approaches. More macroscopic approach, looking at what the macroscopic effect is. And the microscopic understanding would see how they actually work inside the lattice, understand in which way, what kind of defect creates extra levels in the bandgap. That's the dominating effect. And then that leads to a special device design in order to overcome this. I will mostly go into the macroscopic effect with a little explanation of where that comes from in the bandgap, and of course ultimately tell you what tricks we have to avoid the problems to some extent at least. So in terms of lattice, so in this picture you see a schematic silicon lattice with the white dots being silicon atoms. Damage can be that silicon atoms are removed, so you have a vacancy like this, for example. The removed silicon atom will of course reappear somewhere else. So like this one sitting in the middle. You can have larger vacancies. So normally a silicon atom that gets kicked out can cause further damage. So you typically have clusters, as you see it in the picture here. There's one particle coming in here and causing an entire cluster of defect. You may even turn silicon atoms into something else. Those are the gray parts. So you have something like an effective doping from non-silicon atoms. So effect is really like what we did with boron and phosphorus on purpose to achieve p-type and n-type silicon. Those defects are mobile, so they depend on the temperature at which our detector lives. That's called annealing. That is, while you produce a detector, very desirable because you want to move your boron or phosphorus atom in the right place. For radiation damage, that can be nice, may not be. You will see this in a bit. So the net result of all these defects is that your crystal is disturbed, and the disturbed crystal means that your band structure isn't quite as ideal as it was before. So as an effect, you have states within the band gap that should not exist, but of course affects the way electrons and holes behave. So for new states that lie more or less centrally in the band gap, so same distance to conduction valence band, electrons that are in that band gap can more easily move into the conduction band, same oppositely for holes for the valence band, or can be attracted from that. So that's an easier mechanism for generating or recombining electron-hole pairs, which is most notably in an increase in leakage current. So where I said leakage current is created by thermal generation of charge carrier pairs. And of course, if there's less energy necessary to do so, you get more of them. So a net result, increased current, which is a bit inconvenient. You have to supply the current, and the current, of course, disturbs your detection mechanism. So it's, of course, not desired. So not only electrons and holes which are already freely movable can be attracted to those states. Also the electrons and holes from doping, that is states close to the band gap in that case, can be trapped, which effectively changes, of course, the doping behavior. So the free charge carriers that we have for describing the doping suddenly are gone. Something similar, by the way, can happen by changing silicon into something else. Then you might have an effective doping from those newly created atoms. So that is noticed as a net change of the effective doping. And last but not least, if you have new energy levels close to the edges of the gap, so close to the conduction or close to the valence band, the same freely moving electrons and holes that I already had here can be trapped, and that is noticed typically as a loss of charge that is created during our detection mechanism. So the charge from ionization suddenly disappears because it gets trapped in those extra energy levels. So, of course, that means a loss of our signal in the end. So either of this is delicate, and in order to describe this, maybe just very briefly, we need some sort of common scale. So you might know this from ionizing radiation. That's typically described by the dose, which is in the end just the amount of ionizations or charge that is created. Now we're talking about non-ionizing defects, so really a proton or neutron kicking off a silicon atom. That's not based on electric effects. That's really just mostly nuclear knock-on effect. So we need something to describe this here. And the model is that we take basically interaction of the various particles that we have, pions, protons, neutrons, mostly know how much damage they create. That's what you see here on the y-axis for whatever energy is, and normalize everything to the same quantity. So the standard that we typically use is we normalize it to the defect that's created from a Newton at 1 MeV. Then everything that you will see in the next plots is scaled to a fluence, so particles per centimeter squared of the equivalent of a 1 MeV neutron, just to explain the scale that you will see already on this plot. So first effect, increase in leakage current. Well, obviously, the more inner band gap states that you get, the more leakage current you will get. So more or less the leakage current rises with a fluence, so normalized to the 1 MeV neutron equivalent. And that works for various types of silicon material in the same way. Now, that's of course bad. We have to come up with means to compensate the current. That's an electronics trick that we actually apply. We benefit to some extent from what I mentioned earlier on. We have small electrodes, so the effect per electrode is small because the volume beneath is small. The effect, of course, grows with the volume. So the pixel detector actually is intrinsically better in terms of surviving the increase in leakage current. That's a very good part. Now we have extra benefit from annealing. So I already mentioned, with temperature being high enough, the damage in the silicon lattice can move around, and some fraction of that will cure itself. That's what we call beneficial annealing. That's what you see here. So after radiation, and this coefficient basically describes the amount of damage that we suffered during irradiation. If you leave this alone after irradiation for some time, the higher the temperature, the lower the effect goes. So basically that means the lower the leakage current will get. So that's something we can actually actively employ. So as a result, we actively warm up our detector during shutdown times in order to benefit from this annealing, in order to limit our leakage current excess. So that's kind of under control already for our current detectors. Gets a tick. So the next effect was the effective doping concentration change, which you see in those two plots. So there's one oddity. The number of acceptor type states increase with fluent much larger than the donor type states increase. So effectively you're turning your device into P, so the bulk predominantly into a P-type device. If you start with an N-type or with a P-type, doesn't matter, it will always end up being a P-type in the end. That's a bit inconvenient because, well, if you start with an N-type, your substrate will suddenly change behavior, and that has to be taken into account. If you expect your PN junction on well, a pixel segmented side, and suddenly your substrate changes the doping flavor, the behavior changes as well. The other problem is the doping concentration in the end will increase a lot. And remember, doping concentration being high means you have to apply more voltage in order to fully deplete your device. That's what you see on the left y-axis. You very quickly end up with several hundred volts or even 1,000 volts in order to deplete your device. There's one easy, actually found by accident, mitigation effect. If you enrich your device with oxygen during the production, or that is already during the float zone mechanism, the effect of increasing doping concentration is reduced by quite a lot, which we see in the top right plot. So the upper curve is with standard float zone material, and the lower curve is for oxygen enriched material. They simply create different states which have a different influence on the inner band gap states that we have to fight against. So they are more beneficial when you have oxygen combining with the vacancies, for example. So that's what we already applied to our detectors, and that helps us survive. And well, since this should also be mentioned. Now, I already mentioned we have annealing effects. That also works for the effective doping concentration. However, this is beneficial all the time. It can be what we call reverse annealing. When you wait for too long, it turns into the opposite and gets even worse from what you started from. So that's something we have to keep in mind when getting rid of part of our XF's leakage current. We shouldn't overdo it, because then in turn the effective doping concentration will increase and we have to apply more voltages. So there's some sort of compromise in between. So let me skip this part maybe. So last part. Those two effects are with current design more or less under control. The last part has not been such an issue for the current Atlas and CMS detectors, for example, but will become important for the upgrades. So already was for this extra fourth layer in Atlas, and will be more important for the high-lumi LHC detectors, which is the trapping. So trapping, as I said, it means a charge when it travels through the detector is trapped, and trapped means it gets stuck. It will not move any longer. So if you remember the Shockley-Ramo theorem, we only see an induced signal as long as the charges keep moving. The stuck charge will not show anything. That's the problem with trapping. If you don't see the charge, and remember we have to get it close to the electrode in order to make it visible, we don't get a signal. So a high charge trapping probability is bad for us, because the charges will not make it to our electrode and keep moving in order to get us the current we need for detection. So the trapping probability, the inverse lifetime during drift, is shown here as a function again of the fluence, and you see with the fluence again it increases. Also very intuitively, the more trap states that you get in the band gap, the more likely it is to trap your charge. So that's why you get this linear behavior. There's little influence from the annealing. For electrons, the trapping probability decreases slightly. For holes, in turns it increases, but there's not that much of a dramatic effect, so there's little to gain from warmer periods, let's say. And there's nothing else we can do to cure the trapping. However, there are ways to more cleverly design your detectors, and that's what we're currently doing for the upgrade project, or partially was already done for this extra pixel layer in Atlas. So one thing is a clever design of electrodes, which we call 3D pixels. What's the idea? Instead of having electrodes on the surface of your detector, that means top and bottom, where your particle, the charge particle that creates our electron hole pairs, traverses from one electrode to the other, we implement our electrodes into the bulk of our detector. So physically, that means you literally drill holes. You add doping when the holes are open to the outer wall, and you refill it with polysilicon in order to have something conductive. So the final result will look like you see it on the picture. And the clever part here is the drift will work in a completely opposite way and is detached from the volume that you need for charge creation. But maybe let's start with the right-hand part of the picture. That's the conventional surface electrode detector. Your charged particle would traverse from top to bottom, or bottom to top, whichever way around. You have a large charge forming along the track, and then the charge cloud will move to either electrode. So the length of the particle track inside your detector is exactly the same as the drift path of your electrons and holes that are created. Well, I didn't mention this, but the more your particle, so the to be detected particle travels in your detector, the larger the signal, so you can't cut much on that. However, the same distance has to be covered. And well, if you have a long distance, your trapping will act and kill your charge before it reaches the electrode. That's the problem with the trapping. On the left-hand side, you see the 3D electrode design. So you have electrodes penetrating into the material. So again, the particle that we want to detect will penetrate from bottom to top, create electron hole pairs. However, now they can move to either side. So if you're smart enough, we have, let's say, positive electrode on the left and in the middle, negative electrode. Again, charges will be separated as before, but they will move sidewards. And the spacing of the electrode is now completely decoupled from the depth of your detector. So you can still have a large signal from your charged particle going through, but you can have a small distance to be covered by the drift. And that allows you to survive, at least to a certain extent, charges lost by the trapping, because you can collect the charges faster than they would be trapped from the extra radiation damage energy levels. And as a nice side effect, you also need low voltage for full depletion, because you have a shorter distance between the electrodes. You don't have to extend your depletion volume as much. So that would also be beneficial for the increasing effective doping concentration. So here's the proof that it works. The percentage of signal seen compared to fabric new silicon device as a function of the fluence is shown here. And in the most extreme, getting close to 10 to the 16 per centimeter squared, which is round about the fluence that we expect for pixel detector inner layers for high luminance HC, you get a considerable fraction of the signal from what we had originally, and that is on the level of what we see with standard electronics, let's say. So that is indeed feasible. So 3D detectors are a good candidate for future pixel detectors, and actually in some part of this fourth pixel layer in Atlas, it was already implemented. So we have a good, let's say, guinea pig to test it out. There's a little catch. When you have your particle traversing your 3D detector exactly perpendicular, and if you're unlucky and hit one of those polysilicon electrodes, so that's what you see in light blue. So if your particle goes through here, all the charge carriers are created in there, or there's no electric field, so you would not see it. If you hit slightly next to an electrode, you're still fine. You penetrate the regular bulk, the charges would traverse the bulk to the electrodes, and you will be sensitive to the charge particle. That's what you can see here. That's an efficiency map. Red means it's good, so higher efficiency. Green or blue even means low efficiency, and you see the islands exactly match where the electrodes penetrate into the bulk. So that needs to be avoided. For particle physicists, it's easy to make sure you have some sort of inclination with respect to your traversing particle, and they only hit a small portion of your electrodes, which means you're fine. So that makes you survive, and that's what you see in the bottom plot. With a 10-degree inclination, you have only a very shallow decrease in efficiency. So that works out. Right. Let me very quickly go into an alternative approach with the current design that we have. So planar pixel sensors means you have electrodes on top and bottom of the way that I showed it. And well, maybe let's see to this. And there's a very easy trick to make use of the same concept. That is, make your charges go faster to the electrode in order to be faster than the trapping mechanism, which in the end means we increase the electric field. Remember, the drift velocity is directly proportional to the electric field. That means higher electric field. Being faster means less time in the detector, and you get your charges to the electrode before they disappear. So in simple terms, for a parallel plate detector, that would mean you have voltage divided by distance. So you can either increase the voltage, which has its limits. Something higher than, let's say, around 1,000 volts is technically difficult to have realized with connections in a high-density detector. The other part, decreasing the distance, is more or less already what you saw from the 3D detector, but you can also do it in a planar sensor, simply make your device thinner. And there's a little extra trick. You can have very high field regions around the electrodes. So what happens when you make your detector thinner? So thinner is the distance between the electrodes. You can see on this plot. It's the total charge collected from a device. One is 300 micrometer thick, the other one 140 micrometer, versus the voltage that is applied to the electrodes. So if you for low voltages, you see they don't have much of a different behavior, but for increasing voltage, you see the thinner sensor is more efficient, although initially less charge is created because your particle to be detected spends less distance in the detector, so fewer electron hole pairs are created. But that's from the more efficient charge calculation. There's even more to it, so the top left picture is more or less the same, just with an extra red line drawn into. That would be the total ionized charge that we initially expected in the detector. So that looks like there's an effect on top of that, which you might know from Geiger-Müller counters or proportional counters, which we call charge multiplication. So when the electric field gets high enough such that the electrons get accelerated so much that they can ionize themselves, we get even more charge carriers than what initially is there. And that is an indication of this effect. So when you increase your voltage high enough, and that's more efficient, of course, again, with a closer distance of the electrodes, you get this charge multiplication effect. And soon we're back into an effect, into the amount of charge that we had originally. Note all of these detectors were irradiated to affluence very close to what we expect for high Lumi LHC. So that might be a mechanism that helps us to survive even the next generation of pixel detectors currently being developed. Okay, so that brings me to the end. So I hope you saw that silicon is well suited for building finely segmented, in particular pixel ionization detectors, which are employed in form of hybrid pixel detectors. Hybrid means it's a sandwich of electronics and sensors connected by high-density bump bonds, which is used and presumably will be used in the future for LHC detectors. One of the main challenges is the radiation damage to the silicon lattice and also to the electronics, which I didn't talk about, which potentially can lead to a loss of signal, making your detector inefficient. And mitigation can, for example, be achieved, in particular for future detectors, by special design, let it be 3D electrodes or thin planar sensors, which helps to collect the charge despite of things like trapping effects. We have examples already in the new fourth layer, the insertable B layer in Atlas, and this is subject for further investigation for high Lumi LHC trackers. Okay, that's it. Thanks for your attention.
Thank you very much, Jörn. That was very informative. Thank you. Other questions for Jörn?
Like so, you talked about the presence of the oxygen to reduce the charge built up. Is that right? Or
yes, that's correct.
how does that work?
Well, let me dig out. I should have another slide. So the idea is relatively simple. Hang on. I had some backup slides. So we know, here we go. We know from separate measurements, so which I hope you can see right now. We know from explicit measurements what specific inner band gap levels are created when we have radiation damage. There are mechanisms, I have it on the slide, like thermally stimulated current. So basically you freeze energy levels in a semiconductor device and then you slowly warm up the device, and whenever there's a new energy level reached, you get a peak in current. So you know at which energy those levels are. Then you can start playing around with your devices and you see a result in this plot. So wherever you see a peak, you see a new energy level, and you can associate them. For example, the VO means it's a vacancy combined with oxygen. And certain energies are relatively neutral to what happens to our doping behavior. Others will be very aggressive in terms of changing the doping behavior. And that very closely depends on the energy. So basically by forming special states inside the lattice, so the oxygen is really made part of the lattice and can kind of conceal the negative effect of things like a vacancy or a displaced silicon atom. It will still create energy levels that were not there originally, but create them in a different place where they don't disturb us as much as they did before. And the net effect is that you see not as much a negative effect on the effective doping concentration.
Okay.
Jörn, you mentioned several times the closeness to industry. So what is the collaboration between the research institutes and the industries, or is it?
Well, for retard electronics, it's extremely close. Essentially, the collaborating labs from Atlas or CMS, they have chip designers, so you have to know how to design transistors on a chip, of course. They get a huge manual from commercial vendors by how to follow their design rules, basically. So they can basically translate your circuit diagram with a few layout prescriptions into doping profiles. Then you hand it over to the company. For example, IBM was used for the current Atlas pixel detector readout electronics, and then they manufacture the readout chips. That's what we get in turn. So it's really a buy and sell mechanism with the design coming specifically from us.
Okay.
For the sensors, it's almost the same. There's a bit more interaction. Or let's say IBM knows very well how to make chips. There we don't have, well, we have a little bit specific wishes in terms of making them radiation up, but that's well, a very straightforward trick. For the sensors, it's also on a similar level. So we do the design, we being the physics institute. So what's, for example, the size of the pixel electrode, what's around it. We need some special aspects to cover the edges of the sensor, for example, that kind of design. So basically the mask, the doping profile they have to apply. But then there's some sort of iteration in order to get the quality we need for the material. For example, have material that's oxygen enriched. That's nothing that industry would do by themselves. So that was from a close interaction between the sensor vendors. There are normally different companies from microelectronics. Many of them are very specialized into this detection mechanism, so that they're actually conveniently very open to suggest to us. And there's smaller companies, so let's say the feedback between them and us for having special features is a bit more efficient. IBM is probably not as much likely to listen to our problems as a small vendor that makes a large portion of the turnover from our productions.
I see. Okay. And when you showed the picture of these bonds, that you said this is the in the ideal world, but actually it's usually not as perfect. So that means in principle this thing is destroyed, right? There's no way to remove the bonds and try it again. Or is this
exactly, yes. Hang on, that's the slide. So exactly, you say the bond is destroyed. The question is how many of them are destroyed. That's why we have to monitor while we're producing the thing. If there are too many of them, well, let's say normally the destruction is on one side of the object, and for example, in the process that I showed you, the solder bumps, what was it? The solder sphere is applied to the readout chip, which is normally a lot smaller, or at least a bit smaller than the sensor. So what you can do is heat up your device locally, rip off the electronics chip. Maybe I should on the, so as you see from the Atlas module, you have 16 front-end chips on one sensor. So you can, by local heating, basically rip off one of the chips. Normally, most of the solder, especially when they're broken bonds or squash bonds or that sort of thing, they would have not have made contact to the sensor in the first place. So you rip off the defect part, replace it with a fresh chip, and with a very high probability, you can recover the entire device.
Okay. Are there other questions? So everybody's super happy and apparently explanations were very good. Thank you, Jörn. Just yeah, online, nobody's online anymore. Jörn, I guess that's it. Thank you very much for your presentation. That was very interesting. If you don't mind, if you could send us the slides, then I can upload them for the students to have a look later.
Yes, of course, sure.
And then I hope the next time we meet in person again.
Oh yes, I'm happy to come.
So yeah, you know when Carnival is, right?
Yes, I do.
He was here last year. No, 2 years ago, right, for Carnival.
Yeah, exactly. We went exactly for Carnival, on purpose.
Yeah. Well, Jörn, again, thank you very much. That was very cool. Thank you.
My pleasure.
Say hello to everyone in Göttingen, please.
Yeah, well. Okay, and have a nice day, and bye-bye.
Yep, bye.
Bye. Bye.
Bye.
Bye.
So, yeah, that's it then for today's seminar. The next seminar should take place in 2 weeks. However, we don't have a speaker yet. So I'm still trying to get somebody, especially someone from the students, to talk, because that was the original idea. I will send around another email to see if I can convince someone. Yeah, thank you very much, everyone, for coming, and I hope to see you all in 2 weeks. Okay, good.